very quickly. From chapter 17, we said that we can get the delta G under non-standard conditions from this relation. Okay. And last time, our last meeting, we said that delta G is equal to negative NFE. And again, E is the cell EMF. Here is non-standard. I didn't put the little zero here. N is the number of electrons that are present in the redox reaction. So here it was 2. If you remember when we balanced it, it was 2. F is Faraday's constant. Okay, so I can do that. Now, if I were to substitute this value here and the standard version of this here, I would get negative NFE is equal to negative NFE standard plus RT ln Q. And now if I divide through by negative NF and I set T to be 298K, okay, I can solve for E. And I get that E here is equal to standard E, which I have. So if I want to see what that looks like, I can do that. And if I were to divide through, I get that this here is negative 0.0257 volts over N ln Q. And if you don't like ln's, that's cool. You can also have this written as such. Okay, and so this is known as the Nernst equation. And Nernst was a big deal thermodynamicist and physicist and chemist, and he came up with a lot of relations that are used in thermodynamics. And when you take thermo, you will probably see his name peppered all over the place. So let's try to use this to try to get the non-standard EMF for this cell. Okay, and I'm going to be snooty and use the ln, so I'm just going to erase this thing here. Okay, and go ahead and try to use this right here. All right, so my standard cell EMF, I already calculated that. That's 0.05 volts. Okay, this stays the same. This numerator should stay the same. N is the number of electrons present in the redox. I have 2, so it should be 2. And this is the reaction quotient. What is that? What's Q? Right, it looks like an equilibrium expression, but it does not apply at equilibrium. It applies to non-equilibrium environments. So, conditions, sorry. So, that means that though it looks the same, it's not a constant. It just tells me instantaneously what occurs when the reaction proceeds. And just like K, it is products over reactants, right? So products over reactants, I look here at my equation. My products are silver, which is aqueous, mercury, which is a liquid. Liquids get omitted, right? So I only include the silver, so it will be Ag+. The coefficients for silver is 2, so it should be squared. On the reactant side, I don't include the solid. I don't include solids and liquids, only gaseous and aqueous species. And I have Hg2+, plus 2, and it is raised to the first power, so I don't put anything. So that's what that looks like. And what do you think happens? Let me try to a hypothetical. What happens if this value is reduced to, say, 0.075? Okay, this is an example here. So what happens? Just erase here. So real quick, what happens when Ag+ is artificially changed to 0.075 molar? Okay, this stays standard at 1. This goes to 0.075. So let me do that, and it will get squared. 0.075 squared. This stays as 1. And if I were to substitute all of that into